record. We will get recording. So, general announcements first. You should have gotten your papers back. Everybody got your papers back? Give me a thumbs up. Yes, you got your papers back? Okay. Sorry they took so long. It's a pandemic and all, and it was a little hard to find the motivation to grade them, but they are graded. They are done. For those of you who did in-class presentations, I gave you the points that you earned on the presentation. For those of you who pre-recorded, that is on my list for today to watch those. So I will send your score. And to be honest, you have to do something kind of sort of bad in order to not get the full 10 points on the presentation. So I would anticipate that you've gotten the full 10 points on the presentation, but just I'll send you your scores. On the homework, the people who did programming of SHA-1, Dr. Schultz said that he looked at them initially and he has some initial grades, and he said, but a couple of them didn't work and I want to find out why they didn't work. He's like, this is my downfall and this is why I spend so much time on grading stuff. So he's like, can I have a couple extra days to figure out what went wrong, if it's something like big and gigantic or something teeny tiny and little? And I said, yes, that's fine, no problem. So that's the last 10 points of the assignment. So I will get that back to you as soon as I hear back from him as to what his grade recommendation is there. But he said he wasn't worried about any of them. It was probably something little, and SHA-1 is notoriously hard to program. So that is the status of the homework. Final exam, Wednesday at 8 a.m. Wednesday at 8 a.m. I will likely write it out of 150 points. That is my plan, writing it out of 150 points. There will definitely be choices. There will also, and we'll do specific topics in just a minute, we'll do a whirlwind tour. There will definitely be choices. There will also definitely be short answer questions. There is a lot of computation that we've done this semester, but there's also some overarching themes in cryptography that we've talked about all semester. And so we want you to kind of be able to explain those. So kind of a mix between those two things. I don't want to say half and half because then I pigeonhole myself into points, but a division between computational stuff and short answer stuff, general overarching concepts, explanations, etc. Does that all make sense? All right, kind of, sort of, yes, okay. Let me do whirlwind tour and then I'll answer, sorry, there's a bird outside my window. That's now sitting on my light. Okay, all right, sorry, distraction. Let me do a whirlwind tour and then I'll answer questions about, oh, there it goes. Okay, let me do a whirlwind tour and then I will answer questions about format or specific topics or anything here. If you have a question as I'm going through, just unmute yourself and interrupt me because I'm not exactly looking up at the screen. It's a little hard to look at the screen and look at the notes. So if you have a question as I'm going through, just unmute yourself and interrupt me. It's totally not rude at this point in time. Okay. Let's see, way back to the beginning of the semester, we've got the overarching story of cryptography. We got terms, plain text, ciphertext, encryption, decryption, basic players in cryptography. There are 4 possible attacks that Eve has. You should know how each of those works or what information she has. Ciphertext only, known plain text, chosen ciphertext. Kirchhoff's principle. You do not need to know the 1883 version. You do need to know the present day version. All right, that's very important. You don't have to be able to state it exactly the same way that we stated it in class, but you should be able to explain Kirchhoff's principle and what implications that has for cryptography. Types of cryptosystems. We talked about 2 types, symmetric and asymmetric. So you should be able to explain the difference between those. We also talked about, so they're also called private and public key, right? 2 different ways of saying the same thing. And then we talked about the key distribution problem. So you should be able to explain the key distribution problem for me. Simple substitution ciphers. Yeah, be able to decrypt them. I'll give you an easy one, I promise. This is a lot of notes on that. Here we go. Caesar ciphers. You should know how a Caesar cipher works. You should be able to encrypt and decrypt a Caesar cipher. And because this is open book, open notes, you can totally use your letter frequency chart with the graph going up and down, and that will most definitely help you with the Caesar cipher.
Can we use the program we wrote if we wrote a program to do the Caesar cipher?
That's an interesting question. Sure. If I give you a Caesar cipher, it's going to be relatively short. I think there was one on the first test that was relatively short, so I don't know how much your program will help you, but sure, you did the work. I can live with that. That's fine. What you can't use, this is not fair, is an online program to decrypt a Caesar cipher, so no on that one. But if you wrote it, yeah, that's fair. You can do that. Let's see. Affine cipher, I am skipping. You do not need to know affine cipher. That can come off. That is not a topic that I need you to know. Permutation cipher, you should know. So you should be able to encrypt. I won't make you decrypt, like try to cryptanalyze a permutation cipher, but you should be able to encrypt a permutation cipher. Playfair cipher, we are skipping. You do not need to know a Playfair cipher. That can come off. Vigenère cipher, you should absolutely positively know. You should understand how Kaczynski's method works also. If I do a Vigenère cipher, I will give you the distances between repeated strings. It is not productive for you to be counting frantically on the exam. I will give you the distances between strings, promise. You should also be able to distinguish between a permutation cipher, a simple substitution cipher, and a Vigenère cipher based on letter frequencies. So you should be able to distinguish between a permutation cipher, simple substitution cipher, and Vigenère cipher based on letter frequencies. We did that on one of the early homework assignments. The Hill cipher is interesting, but not one that you need to know. So Hill cipher can again come off. We can take the Hill cipher off. Excuse me. One-time pad comes up in this section, so you should know what a one-time pad is, what properties it has, why it's unbreakable, all of that fun stuff. Okay, then we get into number theory. So basically what I'm gonna say, and we'll walk through some of the specifics here, but you need to know number theory in as much as it serves cryptography. So I probably won't ask you any specific number theory problems. I'll ask them in the context of a cryptological problem. Does that make sense? Okay, yes, people are nodding at me. Yes, good, all right. We have divisibility, so how that works. We've got prime numbers. We've got Euclid's lemma. We've got relatively prime. That's a hugely important concept. We've got the Euclidean algorithm. That's also a hugely important concept. If I ask you to find, also extended Euclidean algorithm, if I ask you to find an inverse and I want you to do it using the extended Euclidean algorithm, I will say that specifically. So you should be able to find an inverse by hand, i.e. by using the extended Euclidean algorithm, but I'll make sure that that is specifically listed on the test. Okay, we've got congruences, and again, I'm not going to ask you about congruences specifically. I will ask them in context of a cryptological problem. And that goes with inverses, mod, whatever as well. So modular arithmetic. Chinese remainder theorem. Again, we'll ask it in the context of a cryptological problem. Chinese remainder theorem in the context of a cryptological problem. And then we've got Fermat's little theorem and Euler's theorem. So you should once again know how those fit into cryptography. As you are walking through the topics in the class, where have we used Fermat's little theorem? Or remember, that's the more specific version. So you can say, where have we used Euler's theorem also? I think I skipped it, but Euler phi function, oh no, here it is. Euler phi function is also something you should be able to evaluate, but once again, in the context of cryptography. So Euler phi function. Okay, we then get into key exchange protocols. So you should be able to execute the Shamir 3-pass protocol, and you should be able to execute the Diffie-Hellman key exchange. Again, open book, open notes. You don't have to have these memorized. You can write them out wherever you want to. You can index your notes however you want to do this, but you should be able to execute both of those key exchange protocols. We get into public key cryptosystems. You should be able to give me the overarching narrative on public key cryptosystems. Why are they so important? Why was this a huge development in cryptography? What problems did it solve, etc.? Overarching narrative on public key cryptosystems. You should be able to execute RSA. Should be able to execute RSA. You should be able to talk about the security of RSA. So the easiest way to say this is we had that circle, right, that we talked about. You should be able to, if I dump you into any point on that circle, get to any other point on that circle. And again, you can totally have all these procedures written out. Open book, open notes. But if I dump you into a point on that circle, you should be able to get to any other point on that circle. Tell me that makes sense. You remember that circle that we walked around.
Are you going to make us actually calculate the steps for it, or just you want to show us, like, if you have this, you can do this to get that?
Calculate, be able to execute, be able to execute. Yes, yep. Okay, so that also brings up non-trivial square roots of 1 mod n, and it brings up, there's another one in here. No, that's the only one. Primitive roots are later. So again, I am not going to ask you about non-trivial square roots of 1 mod n in isolation. They will get asked in conjunction with the cryptological problem. The cryptological problem is moving around that circle. Okay, moving on. Digital signatures. You should be able to execute an RSA signature. You should be able to execute an RSA signature for me. Blind signatures are coming off. You do not need to know blind signatures. Again, interesting, but not a super important topic. Primitive roots mod n, you need to know in conjunction with the discrete log problem and the El-Gamal cryptosystem. So you should be able to execute both the El-Gamal cryptosystem and the El-Gamal signature scheme, and that comes in with primitive roots mod n. So you're going to need primitive roots mod n for those particular signature schemes. Okay, digital signature algorithm is coming off. That one you do not need to be able to do. We are taking the digital signature algorithm off. That one is not one that you need. Primality testing. You should be able to tell me the overarching story of primality testing. What's it used for? Why is it helpful? Why is it hard? Why doesn't it always work? Being able to, again, overarching narrative, overarching story of primality testing. You should be able to execute Fermat's primality test and the Miller-Rabin primality test. I am taking Solovay-Strawson off. So you should be able to execute those two. Fermat's primality test and Miller-Rabin primality test. You do not need Solovay-Strawson, okay? All right, and along with that comes pseudo-primes and strong pseudo-primes. So you should be able to talk about both of those concepts, pseudo-primes and strong pseudo-primes. Hash functions. Again, overarching narrative of hash functions. What are they? What are they used for? Why are they useful? What drawbacks do they have? You should know the requirements for hash functions. And when I say no, be able to explain, because you don't have to memorize them because it's open book, open notes. So you should be able to explain the requirements for hash functions. You should be able to evaluate whether a function is or is not a good hash function. If I give you a function, does it meet the requirements of the hash function? You do not need to know how to execute SHA-1. Take that off. Message authentication codes. Again, overarching story. What are message authentication codes used for? How are they similar? How are they different from hash functions? They're kind of the same idea, but they're kind of not. What purposes do they have in common? What different purposes do they have? Requirements, etc. So you should be able to kind of distinguish and again, give me an overarching narrative for those. My research is interesting, but not something I am going to put on the exam. Okay, then we've got secret sharing schemes and threshold schemes. Again, overarching narrative, secret sharing schemes, threshold schemes. What's the problem we're trying to solve? How are these things helping out with that? What issues do they prevent? What issues do they introduce? You should be able to execute the Shamir T, W threshold scheme and reconstruct a secret. So if I give you enough shares, and I promise to make the algebra easy, you should be able to execute the Shamir T, W threshold scheme and reassemble a secret. You can do it however you want. If you want to use Lagrange interpolation polynomials, fantastic. If you want to try to do it by hand, solving these systems of equations, you can do that too. I'm not going to specify how you need to reconstruct a secret, but you should be able to. And then poker over the phone is interesting, but that was kind of an add-on at the end of the semester, so I will not put poker over the phone on the exam. No poker over the phone. That's everything. That was the semester in 12 minutes or less.